graph theory is what we were doing last time. Last time I had sort of made up a bunch of examples of, individual scenarios that you can think of and try to analyze by using a graph. I thought it might be fun to, can we just start off by me asking you all to try something like that? So I would like for you to maybe chat with the people who are sitting near you. Your job is to invent a scenario which can be described by a graph. So I don't know if you remember last time I had ideas like something like a graph where every vertex is a person at the university, like a student, and there's an edge if the two students are in a class together, something like that. So this actually can occur in all kinds of different scenarios. So see if you can invent a scenario that can be described by a graph. Just come up with something. There are many, many possible things. It could be Halloween themed if you want. There's so many options. And then I would like, so you have to tell me, first of all, each vertex is, something or other, right? Like the example I gave last time was each vertex is a student at the university, and each edge represents, in my example at the end last time, each edge was, there's an edge connecting two students if they're in a class together this semester. And then I would like to talk about, for your example, answer me this. What does the degree represent in your example? What is a typical degree in your case? Actually as a number? Remember, the degree is the number of edges which meet each vertex. In my example of students in classes together, a typical degree is something like 100 maybe, 80, something like that. That is the total number of other students that you are in classes with this semester. And then also, is it connected? These are the questions I want you to answer. Now, depending on how weird your example is, your answer to some of these questions might be, I don't know. I don't know what a typical degree is in this graph or something like that. But this is the kind of thing I would like you to think about. All right, chat with your neighbors and friends. See if you can come up with anything, and then maybe after a few minutes I will ask some people to share with the rest of us if I like your examples. All right, go for it. I think you can do it even when it's this early in the morning.
It'd be small, I don't know. Yeah. Yeah. I don't want to keep it still thinking.
All right. You want to go with the Halloween theme?
Yes.
Yes?
Okay.
Yeah.
We can still draw 5 or just.
You guys got any ideas? All right. You're going to go Halloween theme? So many options. Any ideas there?
Yes, just yeah. I did this in high school, so I was each edge represents what or like 5 feet.
Like a building?
Yeah. And it's
Two buildings have an edge.
like person like 1.
And then person two to skip. And then there'd be a line.
So there's an edge deflect there with the student.
Yeah, it would just have to be more specific. I don't know how to say it.
I was like, oh.
Yeah, so think about what would they be doing? One with bigger degrees and one with smaller degrees.
Each represents a different.
Any ideas? Your team of one? All right.
Well, it'd be like, it could be like two.
Us fellas gotta stay together, right?
We'll just be like
So maybe you got
like each edge represents have that be like a similar, the same. Like each edge represents like the same.
Oh, yeah.
Yeah.
and two drinks are related, what can make two drinks?
Oh, yeah. I feel like the Joker was yeah, the Joker.
So there's an edge between two drinks.
Yeah.
So you have two different drinks, right? So your graph, like here's pumpkin spice latte and here's.
Because otherwise if you just draw the line, yeah, then it doesn't say anything.
A clown.
Alright.
Yeah. Because it's like so. Or.
Okay, that will work, yeah. And then try and think about these questions. Is that connected? Is it et cetera?
Clown and ghost.
We don't draw the line.
You guys got any ideas back here?
No, we don't know, and the line saying, oh, they're from the same movie or whatever movie it is.
Okay.
So I guess.
And what decides if it's edge or not?
Then we could do like instead of like 5 people, it could be like all the trick or treaters.
So you have like some sports, right?
Okay.
Say like golf.
Oh,
Five
then
of
we can do
There'd be an edge.
like this. And then, but then there's like,
Yeah, that's an edge. And why? They both have a ball. Okay, what if one has a ball?
something that connects like
Because they both don't have.
the Joker and the Metropolitan.
So like, should there be an edge between golf and volleyball? And then so like, where is like track on this graph? Right. So I think the track is like a dot, just all by itself, right?
Because it makes a path. Oh.
You guys getting anywhere? Any ideas? Yeah. So as a graph, you think of
And then
and then you have to think about what, how do you decide?
yeah, sure.
Right, this person has to be a villain.
Yeah, we'll start with 2 and then the last.
Okay, sure. So like you and you are each a person. Is there an edge between you?
Okay, so I don't know any other.
You are? Okay. It's already happened? Are you thinking about this weekend? Okay. All right, yeah, so if you dress as the same thing, then there's it. Yeah, all right. Okay. Sure. Get anywhere?
Yeah.
You guys, what you
Wait,
got?
not just name.
Does he wear a mask?
3. Let's also do Snickers. Snickers.
So
slash.
each vertex is a person?
Well, you have to
Okay,
wear a mask.
and then there's an edge.
Okay, so let's we actually want to be. So should we connect it?
Okay, yeah.
Wait,
Two
should we
people go to
connect
the same
it?
place.
Should we do one
In the center
like
of the
is
vertex?
currently
Sure.
separate?
How do I connect it?
Like on its own. Like is it
Yeah.
All right, maybe we can, it seems like people's conversations have run their course a bit. I heard some interesting ideas. A lot of people wanted to go with the Halloween theme, which is great. Anybody have a great idea they would like, they are really proud of? I heard a lot of sort of confusion sometimes about these, but let me just, I'll mention one that I just heard a moment ago. This is a Halloween theme. Let's say each vertex is a person, a trick-or-treater. All right, and then you have to tell me what makes an edge between two vertices. Now, when you're thinking about a graph, an edge always goes from one vertex to another. This is a bit of a confusion that I heard as I was walking around. You should not say something like, each vertex is a trick-or-treater, and you get an edge if you're dressed like Shrek. Because an edge goes from one to another, right? So you have to tell me, if there's two different trick-or-treaters, what makes it so that those two are connected? And you don't just say Shrek. Shrek is like a thing that one person is, right? It's not two. These folks said, which I think was a good one, each vertex is a trick-or-treater, and they get an edge. Well, let me say, just to be more clear, based on what I just said, two verts have an edge if they went to the same house while trick-or-treating. All right? So, you know, Billy and Tommy are two different trick-or-treaters. If those two guys at some point stopped at the same house, then they get an edge. And if not, then they don't. This is defining the graph. I think this sounds great to me. Can we say something? I don't know who came up with this. Were you thinking about just like all trick-or-treaters everywhere in the universe? I guess so. Let's just say all kids everywhere, all the children across this great land, they have an edge if they went to the same house. Do you think, so these questions, can we answer any of these questions? Now, for this example, I would say some of these questions are kind of unanswerable in this case, just because I don't actually know much about statistics of trick-or-treaters. But what does the degree represent? I would say, in this case, the degree of a vertex would be how many other kids went to the same houses as that kid. And this is a number, right? Each individual vertex has a degree. So here the degree is the number of other kids who went to the same house. Maybe just to be very clear, I'll say the degree of some vertex called x is the number of other kids who went to the same house as x did, right? And what is that number typically going to be? I also wanted to ask, what is a typical degree? Is a typical degree something like, 10 or 50 or a million? I would say it depends a lot on like how big these towns are and how many kids there are walking around. I don't know, maybe 20. Like if you as a kid go to one house, the degree of you is how many other kids went to. Maybe more than 20. I don't know. I'll just say, hard to say what that number is. It's not like one, right? It's probably more than that. It's the number of other kids who went to the same house as you did when you were trick-or-treating. It's probably like in the hundreds for a small town with a lot of kids walking around. There's probably a lot of that. Great. Is it connected? This means for every kid in the whole universe. Maybe those two kids didn't go to the same house, but can you say like this kid went to the same house as this other kid, and they went to the same house as this other kid, and eventually end up with any other kid anywhere? I think this is almost certainly not true. Like for instance, there are kids in Hawaii. None of them went to any kind of same house as kids in California, right? Because they don't get around that much, right? I will just say probably not connected. I would say not really obvious, but probably not connected. All right, these are my thoughts about that graph. Can we have maybe one more example? And then we'll talk about some other stuff. Anyone like to volunteer? I heard some decent ones as I was walking around. How about I liked yours actually. This was also about trick-or-treaters. It was let's say here's a new example. All right, let's say the vertices again. The verts are trick-or-treaters again. This time, two vertices have an edge. When they wore the same costume. That's the rule this time. Two vertices have an edge when they wore the same costume. All right. So again, we should think of, can we think about what does the degree represent this time? Here, the degree. So what that means is like, you know, a little piece of the graph might look like something like, you know, Jim, who was a Shrek, is the same as Nick, who was a Shrek. I don't know why I'm on Shrek today. Right? They get an edge, but, you know, Jill, who was a Fiona, that's the girl Shrek, right? She would not have an edge to those Shreks. All right? Because she has a different costume than those Shrekses. All right? This is what a little piece of the graph looks like. Can anybody describe in words what does the degree represent here? The degree of x is, it is a number. Can anybody say in general terms? Like this, in this little piece of the graph, the degree of Jim is 1 because there's one other person who is also a Shrek, right? What can you say just in general terms what the degree represents then? It's something like the number of what? Yeah?
Kids that have the same costume?
The number of other kids who have the same costume as X, right? If X is one of the vertices, the degree is the number of kids, I will say other because that person themselves doesn't count. The number of other kids with the same costume as X. Yeah, great. Do you think this graph is connected? Like my little piece of the graph here, which I drew, is not connected, but that's because I only drew a few things. Maybe, is it possible somehow like Jill is connected to other things maybe? And then these at some point actually do wrap around and get connected up with these guys? Or is it not connected at all? I think we can answer this question actually. Is the graph connected? Nope. I agree. Why not?
Because they each only have like one costume, so it's not like somehow Fiona will connect to Shrek. If they had multiple costume changes, then maybe.
Right. Yeah, certainly no one would have multiple costume changes. Yeah, everybody connected to the Fiona has to be another Fiona, right? And there's no way to, even if you hop across several edges, you're not going to end up at Shrek's if you started at a Fiona, right? You have to just hop over to other Fionas. So this one is not connected, right? That's because no path, well, can I say something somehow like this? Any path from a Shrek can only lead to other Shreks. Right? So there's like a little cluster of Shreks and they're all together, but then there's also a cluster of Fionas and they're all together, and you got, you know, Annas and Elsas or whatever, which cannot be connected with one another. They are all connected to each other, but not to the other parts of the graph. All right, excellent. Thank you for your Halloween-themed graph ideas. Not everybody's were Halloween themed, but when you're trying to come up with these, it's just you say what the vertices are, and then you have to have some connection between two vertices. Excellent. I think that's enough examples. I mean, I don't want to spend the whole time going around with everybody. Can I just say a few more like actual real life examples where graphs are really useful? I would say, you know, you can express this as a graph, although doing this, you know, on some level nobody really cares about this graph about costumes or something. It's not terribly important in real life, but I thought I'd just sort of shout out a few real life IRL important graphs, or places in real life where analysis of graphs is actually meaningful and important in our real lives. So all of the ones that we've been talking, not all of them, but many of the ones that we've been talking about fall in the general category of social networks, right? These social networks would be graphs in which the vertices are individual people and the edges represent some kind of relationship between the people. So like the classics, you know, as far as like, you know, online digital social networks, the classic one is Facebook, where you had individual users which might be friends with each other on Facebook or not, right? And so in social networks, the vertices are people, and then edges represent some kind of relationships between those people, or friendships. I suppose it could represent other things than friendships, but some kind of relationships between them. And then the degree of a vertex is basically like how many friends that person has. How many edges coming into a vertex tells you how many friends they have in the social network. And so, you know, if you're on Instagram or something and you're trying to get a lot of followers, one way of thinking about that is you are living in a graph and you're trying to increase the number of edges, other people that are connected with you in this graph. All right. This so like if you really wanted to do some kind of statistical study of users on Instagram or on Twitter or something like any of these social networks, graph theory is the way to do that. That is the fundamental framework by which you analyze things like that. I was also when I went to grad school in Los Angeles, and I was like on my way to school every day, I would pass an HIV testing clinic, and I never went to this place, but apparently when you go to such a place, they ask you to, you know, you take a blood test or whatever, and then they also ask you to list, if you are willing, list your sexual partners, so that in case you test positive, they can contact these people, or maybe these people already exist in their database, and that's useful information. This also is a scenario which, if you wanted to do serious analysis, you would analyze in terms of a graph. So each individual person, as I was walking around, somehow nobody said this, each vertex is a person, and there's an edge between those people. If you know what I'm talking about, if those people have had, in the biblical sense, relations, right? This is a super important graph. I mean, the people who participate in this kind of graph this is like serious consequences to the structure of the graph. And what's important in that graph is there a path from one vertex to another? Because if one person is positive and there's a path to you, there's trouble, right? It means that you have possibly been exposed to the virus. The degree of a vertex in that graph is also important. Somebody with a super high degree means they've sort of been getting around, if you know what I mean. And this, I don't know, you know, no judgment, but in the context of this graph, that's probably a bad thing. You don't want to, in the HIV graph, you don't want to have a lot of connections to, certainly not to positive people. All right, anyway, this is super important, not just for like Facebook, which is at the end of the day kind of a recreational thing, but it's also the way that we analyze actually important things in real life. How about, I got like completely different examples. How about computer networks. In this case, the vertices would be just like individual computers, and I don't necessarily mean like desktop or laptop computers, but even like your phone or whatever. The vertices are computers. And an edge, the edges represent, network connections, right? So like we probably all have phones which are right now connected to the cell phone network. Your phone might also be connected to the campus Wi-Fi network here. Now, if you ask me like, is it possible for me to send a text to you with our phones? The answer is yes. I mean, I don't have your phone number, and let's be honest, I don't need your phone number. But yes, I could send a text to you. That's not because there's a direct edge from my phone to your phone, but it's because my phone can go to the cell network. The cell network somehow is connected to your cell network, and then your cell network connects to your phone. So it's not that there's an edge directly from my device to yours, but there is a path somewhere in the internet from my device to yours. So paths are super important. And it is usually desirable for these networks to be connected, right? That is to say, it is in theory possible to get from my phone to your phone. If that weren't the case, then that would probably indicate something was wrong with the structure of the network. Anyway, analyzing computer networks, I'm sure you can agree, is super important. And there are a lot of people who really care about analyzing computer networks. And the way you do that is in the language of graph theory. All right, I got one more example. I'm sure you could think of many, many more examples in real life. How about road maps and navigation? This also is fundamentally expressed in terms of graphs. So in this case, vertices are specific like addresses in the real world or intersections, and edges represent the roads or whatever else you're trying to navigate across, right? So it's like you have a bunch of addresses here, and they're all connected by roads, and sometimes there are intersections which go off to other roads, and sometimes they do stuff like this, right? This is what a typical road map could look like. And the whole idea of like the lady who gives you directions while you're driving, what she is doing is she's looking at this graph for paths from one vertex to another. So you say, I want to start at my house and I want to go to Bobby's house. The lady in the GPS will find a path in the graph from this location to this location. And then as you go, she tells you which way to go. All right, so here, path finding is the most important thing. And in fact, it's not good enough that the lady tells you a path. The lady's goal is to tell you the best path from one place to another, where best means the shortest path, right? And so there are actually people who study path-finding algorithms in graphs. This is a super important real-life question that that could affect, your real life. If somebody somehow discovered a better way to find paths in graphs, then they could improve all of our GPS ladies. Mine's always a lady. I don't know if you all. Sometimes the default is a man. I switch it to a lady. I don't know why. I prefer the lady. All right. These are all the kind of important real-world examples that I could come up with. But I'm sure that anybody could think of more. One general principle that seems to be more or less true is graphs tend to be used for analyzing kind of social constructs or like inventions of people. All of these examples that I've given here are all about kind of people, man-made things, if you will. Unlike, say, physics, right? Like if you want to study mathematically the laws of physics, you should learn calculus. But if you want to study mathematically relationships between people or anything like that, you should learn graph theory. This is the appropriate mathematics for that kind of thing. It does not involve, these kinds of social contracts don't generally involve calculus, but they involve graphs as a fundamental approach. All right, great. Any thoughts about that? I'm sure you could think of more and more examples of where graphs come up in real life. They are super important. I would like to say something about sort of technically, let's talk a little bit abstractly here. What is a graph? Really? Really now? What is a graph exactly? I hope everybody has an idea of what a graph is. I said last time what a graph is a diagram, you know, like this. Like this is what a graph is. Where, you know, maybe I'll give names to these things, A, B, C, D, E, and let's say they're connected up like this. And maybe there's another one over here, right? So far, this is the level at which I have explained what a graph really is, all right? It's a thing like that, okay? This is a graph. Now, this actually is not a great, mathematicians don't like this as a definition of what a graph is. So if your little brother asks you what a graph is, you should say, well, you know, it's like something like this with the dots and the lines and all that. And your little brother will understand what you mean, and everything will be fine. But actually, this is not a great definition here. Why not? You could ask, here's a question, is that the same as, I'm going to draw this again, A, B, C, D, E, F here. Whoa. How about that? Are they the same graph? The answer is yes. Mathematically speaking, these represent the same graph because all we care about is what are the vertices and where are the edges going? Like what are the connections between the various vertices? And this one has exactly the same connections as this one. Now, your little brother, when looking at this, will say, no, of course they're not the same because this one has this silly curvy thing and this one has a straight thing. And at some level, I would agree with your little brother. Like purely geometrically speaking, they are not the same. There's a real difference between a straight line and a weird curvy line, and these are not the same. Is that the same as this? The answer is, in all of these settings where we're trying to represent real things using graphs, we want to view these as the same. Because, like I said, all we really care about are what are the vertices and which ones have edges to which other ones, all right? How you draw the lines is not important in drawing graphs. That's why every time I drew a graph up here, if you were copying it into your notes, you don't have to copy it like exactly the same geometry as what I drew. All that matters is where are the dots and which dots are connected by lines, right? So we want to view these as the same, and what that means is the graph is not exactly a diagram, right? Because those two things up there, those are different diagrams, but we want to judge those two diagrams as representing the same graph. So that means when I talk about a graph, I do not actually mean a graph is one of those diagrams. A graph is some kind of concept which is represented by a diagram, but what is the true nature of the graph? I will say the graph is not exactly a diagram. Its sort of true nature is more abstract. This is like you begin to sound like a stoner when you talk about this, but it's like, no, man, it's not about how you draw it, man. There's like a deeper reality behind it, underneath it, within it, like it's in your heart, man. It's like all about the journey, right? The true nature of a graph is not actually the picture. So I would say in a more technical kind of abstract, mathematically appropriate language, I would say these are two different pictures of the same graph. But when you ask me what is the graph is not the picture. The picture represents what the graph is. okay, in that case then, what really is the graph? I would say the graph is just, there are six things here, and they are connected in certain ways. That's what the graph is. It is how many things are there, and how are they connected to one another. And if you like, you can draw a picture of those connections, and that's what this is, and that's what this is. But the picture is not what the graph really is. What it really is just a bunch of stuff which have connections. So here is all of this to say, there is a real definition, which I will write now. The real definition of a graph does not involve pictures at all. The pictures are only a representation of what the graph is, but the graph's true nature is not a picture. It's an abstract thing. And all it is the real definition of a graph. All right, a graph is a pair of sets the vertices and the edges. A pair of sets. There's two sets. The vertices and the edges. And that's it. All right? If you want to, you can draw a picture of it, and the picture is a representation of the graph. But the picture is not what the graph really is. What it really is just a set of vertices and also together with a set of edges. Now, we are almost never going to use this point of view. Like when you work with graphs, usually you just want to see the picture. And that's usually how we're going to do it. But if we want to really talk about the graph formally speaking, so let me say, I'm going to draw this same one again here. A, B, C, D, E, F. All right, this is a graph. That's the picture of the graph. The true graph, and this, to distinguish this from talking about pictures, we're going to call this the formal description of the graph, which does not actually involve the picture, is, you say, the vertices are the set, and when mathematicians write sets, that's kind of ugly there, we use this curly bracket thing, like that. And what are the vertices? They are A, B, C, D, E, F. Okay, so that's the set of vertices. And then I also have to tell you the set of edges. And these edges is also a set, so I use this curly thing. And the edges themselves, I'm going to write as just, there is an edge from A to B. And the way I represent that is as a little pair, a little ordered pair, A to B. All right? So there's an edge A to B. There's also an edge B to C. And you just have to write them all down. There's an edge B to C. There's an edge C to D. There's an edge D to E. There's an edge E to A. And there's also an edge E to F. And those are, I think I wrote down all the edges. There are 6 edges here. All right? This is the formal description of what the graph truly is. All right? So this is a very easy homework question or even a test question. I believe this is one of the, I think this is one of the things on our list. I could show you a picture of a graph and say, give me the formal description of the graph. It's this. All right? You have to write down a set of all the vertices and then a set of all the edges. This is essentially always easy to do, and there is never any kind of funny business. There's no like weird looking picture that would make this hard to do. You just write down a list of the vertices and you write down a list of the edges. All right? And you can also go the other way around. So I could give you a formal description and then say, your job is to draw me a picture of this graph. So maybe we can try that right now. And this, like I said, this is always going to be easy. So I think maybe I will just have you guys try and do this one. So draw the graph that looks like the vertices are A, B, C, D, and the edges are AC, BC, AD, CC, and BD. So the only slightly weird thing here is there is an edge called CC, and I'm not sure any of the graphs that we've done so far have edges like this, but what that means is somewhere in your graph is a C, and it has an edge looping around back to itself. So this is allowed in graphs. I don't think we've seen this before in our other examples, but anyway, that's what this CC means. It means there's an edge from C going back to itself, which looks like that. Anyway, see if you can draw the rest of this graph. There are 4 vertices, A, B, C, D. One of them is C, and it has this little loopy loop on it. Maybe I'll walk around and see how you're doing. There's not a lot to it if you know what you're doing. I'll give you 1 more minute on that clock, and then we can talk about it. Show your picture to your friends. See if they got the same thing, if you like. All right, has it been a minute? I think it's been about a minute. So you should just start, you know, when you begin, you have no idea what this is going to look like, but it has 4 vertices, so I would just start by making 4 vertices and call them whatever you like. A, B, C, D, maybe like that. Now, you might have called them in a different arrangement or something, which is fine. I have an edge, all right? Now I'm just going to go down the list here and just make edges for all those. A to C is like that. B to C is like that. A to D is like that. C to C is like that. And B to D is like that. There you go. This is what the graph should look like. Right? I hope you got a picture that looked something like that. Or, actually, your picture may not have looked like that. Like, what if, when I drew the graph, maybe I labeled it, for some reason, this way, A, B, C, D. I don't know if anybody decided to label it in this way. Now, it kind of, the picture of it will look kind of different. So now I go A to C, B to C, A to D, C to C is this loop here, and then B to D. I guess that doesn't look very different, but I mean, they are in a different arrangement. What if instead I did, I don't know why I would do this, but what if I did A, D, B, C like that? Then it would go A to D, B to D, C to A, then it would look like this, right? That one maybe does look pretty different from the other ones, but anyway, these all represent the same graph. They are just different pictures of the same graph. So all these are, you know, none of them is wrong or anything like that. All of these are just different pictures of the same graph. Right? Is the graph connected? The answer is yes. All of the vertices are sort of in one big blob, one big chunk. But actually, one thing to notice is when you look at this, if I just show you this and ask you, is it connected? It's actually not easy to answer that question until you've drawn the picture. Just by looking at this list of edges, it is not obvious if it's going to end up being connected or not. You really have to draw the picture to get a feel for that. All right. Great. We got about 5 minutes remaining. I think we can talk about one sort of super important historical example. This is actually, in many ways, the OG graph theory example. This was considered in the 1800s by the famous mathematician named Euler. This word, this name, this is a German guy named Euler. Don't say Euler. You sound foolish if you say Euler. This person's name is Euler. If you say Euler, I will say Euler. It's Euler, all right? He's German. Now, don't get it twisted. You may have also heard of this mathematician, the father of the ancient Greek geometry, Euclid. That's because he was not German. This is German, Euler. This is Greek, Euclid. Is that more confusing? Anyway, Euler. Euler actually was the guy who more or less invented graph theory as we now understand it. To me, it's a little bit surprising that this is such a recent invention, like far newer than calculus and other kinds of very sophisticated math had already existed up to this point, but people hadn't really done graph theory until the late 1800s. Maybe because graph theory really is only important when you're trying to analyze, like I said before, sophisticated social structures, and it was not really thought that mathematics was appropriate for those kinds of questions until more recently. Everybody has always done geometry and physics using mathematics, but it wasn't. It took a while for people to realize that this was actually possible in other settings. But anyway, Euler first considered this specific problem. This is referred to as the 7 bridges of Königsberg problem. Apparently, this was like a popular kind of meme math problem that people would chat about in the city of Königsberg, which is a European city. Here's the scenario. There's a river going through the center of the city. So this is a river. That's the water, right? There's sort of part of the city on the top and part of the city on the bottom. And there were 2 islands, here and here. And these islands had 7 bridges connecting them in various ways. And the bridges went like this. There's a bridge here. There's a bridge here. There's a bridge here and here. There's also a bridge connecting them across the middle. And the ones on the island on the left actually had 2 bridges each to the mainland on either side. All right? And there are 7 bridges. And this was popularly, like, people used to talk about the 7 bridges in this city. And one kind of thing that people used to chat about is this question. Is it possible to walk each of the 7 bridges once, exactly once? You could phrase this in terms of some kind of pub crawl, which often people do. Can you like start at the bar down here at the bottom and walk across each bridge one time so you don't miss any and you also don't repeat any? Can you walk each of the 7 bridges exactly once, no repeats? And end up where you started? This is the question. This was a popular thing that people used to talk about. And just looking, anybody see how to do it? Let's say you start at the bottom, right? You can go sort of, I'm going to try and draw my dot with the tail. I can do with the tail. So if I start down here, maybe I go up here, and then up here, down that one, Actually, that was bogus because I get stuck up here, right? You're not allowed to repeat any of the bridges, but you're supposed to go across all of the bridges. So maybe I'll do this first. This is also a bad solution because I missed one of them. All right, this is the idea. Euler proved it's impossible. And how exactly did he prove that? Basically, he invented graph theory and used graph theory to analyze these connections here. All right, we'll talk more about this problem and how he did it next time.